Hey everybody, Dr. A here, and in this video we're going to be exploring an example of how to develop a position vector. So let's go ahead and get started. In the given information, we're being asked to express the position vector r as a Cartesian vector, then determine its coordinate direction angles. So let's go ahead and look at the 3D figure that we're given here. Here we see we have a positive x-axis branching off here. We have a positive y-axis branching off here, and we have a positive z-axis coming up here. Now the position vector that we're interested in is this red vector in this particular three-dimensional sense, and it is extending from point A to point B. Okay, so that's what we're looking at here. Now these other measurements and angles that you see on this figure are the measurements and angles that are defining these 2 points, A and B. Okay, so let's look at each one of these individually and see how we can piece this all together. First, the point A here is below the XY plane, okay? It's below that XY plane, which really means it has a negative Z component, okay? So this point A here is got a negative Z component that's defined by this little dashed line right here, okay? Now, if we were to extend a little help line or a projected line from the origin to point A, that's this green dash line we have here, okay? Now, that green diagonal line that is sweeping from the origin into the negative Z direction is gonna have an angle of 20 degrees. That's what we see here. That's a 20-degree angle, and it's forming this little green right triangle here, all right? And we're gonna have to analyze that triangle here in a minute. Now, if we were to project that little help line here, this green dash line, up to the XY plane, we'll get this other green diagonal line here, okay? Now that line is what I sometimes call the shadow or the projection in the two-dimensional XY plane, and it has a reference angle of 30 degrees away from the positive y-axis. So as we go through the solution of this problem, I'm going to take out and kind of extract these elements here to help us visualize it better. Okay, but that's how point A is being defined, by these two reference angles, a 30-degree angle that's in the XY plane, and then a 20-degree angle that's sweeping into the negative Z direction. Okay, now the diagonal length from the origin to point A is 5 feet. That's this 5-foot length right here. So again, that's that diagonal length here. Now, what about point B? Point B is actually in the YZ plane. So if you notice, we have some dimension lines that are defining the location of point B. So if point B is in the YZ plane, that means that it has a 0 x component. So it does not have an x component. It's going to have a positive 7-foot dimension as a y coordinate. So you see from the origin in the direction of the y-axis, we have 7 feet here, and then it has a z coordinate of 1.5 feet. So we're going up in the positive z direction, 1.5 feet. And so the position vector that we're interested in is extending from that point A up and over to that point B, okay? And that's what we're trying to investigate, is what's going on with that position vector R, all right? So let's go ahead and write solution. And what I'm going to do is I'm going to say, okay, if I want a position vector in 3 dimensions, okay, I'm going to say R equals, and what we do is we basically say the second point minus the first point, and we do that for our x, y, and z coordinates. So I can write this as x, the x coordinate of point B minus the x coordinate of point A times I, and then plus the y coordinate of B minus the y coordinate of A times J, it's a J right there, and then plus the z coordinate of B minus the z coordinate of A times K. All right, and if you're a little rusty on that, go back and see my previous background video on this. So the work we've got to do here is really getting these coordinates, right? The x, y, and z coordinates of the 2 points, A and B, all right? Now, more specifically, the work we have to do is getting the coordinates of point A, because you see that's defined by these 2 angles. If you go back several videos, when we talk about three-dimensional vectors, those are angles like phi and theta that we talked about several videos back. So let's go ahead and kind of catalog the easy parts of it first. We can go ahead and just say, hey, we know what point B is, right? Point B, and we saw it just a minute ago as I was going through it, point B has a set of coordinates of 0, comma, 7 feet, comma, 1.5 feet, okay? And we said we know that because point B is in the YZ plane and does not have an X component, okay? So if we want to check off, put little check marks here for point B, we can certainly do that, okay? Now what we really need to do is find the coordinates of point A, and we're going to do that just using some basic trigonometry, utilizing these 2 angles, the 20-degree angle and the 30-degree angle. So the first thing I'm going to do is I'm going to say, hey, let's look at a 2D view, okay? So 2D view, and what I'm going to do is I'm going to peel out this right triangle right here, okay? This is the right triangle that's dipping in the negative z direction at a 20-degree angle, and I'm going to look at that in 2 dimensions. So if I do that, what am I going to see? Well, I'll see that length there. I'll have another length here, and I'll have that diagonal length there. Well, this diagonal length, that's that 5 feet, okay? So that's 5 feet. And then what else do I know here? Well, I know that this is that 20-degree angle, and this is a right angle here, okay? And so what can I do to get these lengths that I'm interested in here? Well, I'm going to do some right triangle trigonometry, okay? And so I'm going to call this dimension right here A sub z. And, or let me back that up. We're going to call that, I guess z sub a is a better thing to call that, right? Just to be consistent with my labeling here. So that is the same z sub a that that I'm interested in my position vector. And that, what is that? That's just this distance here, okay? So again, I'm peeling out this right triangle, and I'm going to get this distance here. That is ZA, all right? What about this dimension up here? Well, I can give this a name. Now, in our previous videos, I believe we would have called this maybe A prime, okay? And the prime is just kind of just a label, but that's indicating that that's the shadow of this diagonal, right? This hypotenuse being cast onto the XY plane. And here I can do some right triangle trigonometry to solve for these, right? So what can I do here? Well, I can say A prime is going to be equal to 5 feet times the cosine of that 20-degree angle. And then I can get Z sub A is 5 feet times the sine of that 20-degree angle. And so I'm going to get out my calculator, and I'm going to punch that through. When you do this, make sure your calculator is in degree mode. So we'll say 5 times the cosine of 20, and I get 4.7 feet. I really get 4.698, but we'll call that 4.7. And then I'm going to say 5 times the sine of 20 degrees, and I'll get 1.71 feet for Z sub A. So now I can check that off, right? I can check off that Z sub A because I know it now. What about XA and YA? Well, now what we've done is, since we have gotten this 4.7 feet, which is A prime, which is really this length right here, this diagonal line on the XY plane, what I can do now is peel out this right triangle that's in the XY plane that contains this 30-degree angle, and I can look at that in 2 dimensions, okay? So how about I do another 2D view, all right? Another 2D view, and I look at that triangle that's in the XY plane. So what am I going to see whenever I peel that out? Well, again, I'm going to see another right triangle here. And this is me looking down. This is me looking down on the XY plane at this right triangle here, all right? So if I label things accordingly, I know that this is a 30-degree angle, this is a right angle here, and then where is that A prime? Well, that's this length right here, A prime. So this A prime, remember, is the same as this, okay? We're just looking at two different triangles that are connected together somehow, all right? So I know that A prime is 4.7 feet there, all right? What about this XA and ZA? Well, I'm sorry, XA and YA. Well, XA is this length right here, and YA is this length here, all right? So this is the YA length, and this is the XA length. And similar to what I did before, I'm just using right triangle trigonometry, and I'm going to be able to say that YA is equal to that A prime, which is 4.7 feet, times what? Times the cosine of that 30-degree angle. And then I can get XA is that A prime, which is still 4.7 feet, times the sine of that 30-degree angle. So if I punch this in, let's see what we get. 4.7 times cosine 30 is 4.07 feet. And then I'll have 4.7 times sine of 30. Again, you're in degree mode, 2.35 feet, okay? And so now, what do I have? Well, I can check off that XA and that YA. So now I can piece all of this together as my position vector, okay? So we're going to say R vector equals XB minus XA times I, which, what is that going to be? Well, XB is 0 minus XA, so minus 2.35 feet times I, and then we're going to look at the J component, so we'll say YB, which is 5 feet, minus YA, 4.07 feet, times J. And then we're going to look at the Z component. Now here's where we got to be careful, right? It's ZB, which is 1.5 feet, minus ZA, okay? But remember, this ZA, 1.71 feet, is actually already negative, right? Because it's going into the negative Z direction. So when we say ZB minus ZA, we're really saying 1.5 feet minus a negative 1.71 feet, okay? And then times K. Again, this is really a negative component when we're looking at it in 3D, okay? So even though I left off the negative here for the sake of geometry, you know, we can make sure we note that that's actually a negative belongs there, okay? So when I start piecing this together, what do I get? Negative 2.35 times I, and then plus 7 minus 4.07 is 2.93 J, and then 1.5, and it becomes plus 1.71, and so that becomes a plus 3.21 K, and collectively we carry units of feet. Now that's our position vector as a Cartesian vector, but we need the coordinate direction angles, right? So if you remember, how do we get coordinate direction angles? Well, we take the arc cosine of each component over the magnitude of the vector itself. So in order to get the coordinate direction angles, we really need the magnitude of R, where we apply the Pythagorean theorem. So I'm just going to go ahead and do that in my calculator. 2.35 squared add that to 2.93 squared, add that to 3.21 squared, and then we square root that, and we'll get the magnitude of r is 4.94 feet. And so we can get the coordinate direction angle alpha is the arc cosine of rx over the magnitude of r. And then beta is the arc cosine of ry over the magnitude of r. And then gamma is the arc cosine of rz over the magnitude of r. And we can go in one at a time in our calculators. Don't forget that negative 2.35 over 4.94. So I get 118.4 degrees for alpha. And then I got arc cosine of 2.93 over 4.94. That comes out to be 53.62 degrees. Then I've got arc cosine of 3.21 over 4.94, and that's 49.47 degrees. And you could round those to 3 sig figs, just to keep track of your sig figs a little bit more appropriately. But regardless, our answer is this Cartesian r vector and these coordinate direction angles. So if you found this video helpful, please hit like and subscribe, and be on the lookout for other content like this. Thanks for watching.